All right. Well, hopefully you found that interesting. I just found out this summer that my one of my elementary school teachers has prosopagnosia, and she was really surprised that I knew the word. She dumbed it down for me and said it was face blindness, but I'm like, oh no, that's prosopagnosia. I'm familiar with that, and she was not even aware. 10 years after the event that caused the prosopagnosia, she was not aware that it occurred because it was a specific part of her brain that received the damage, and that it's not about memory. It's about this area of the brain that is designed to interpret faces and to recognize faces. And she said, but why do I recognize voices? And it's like, because you don't have a specialized recognize voices area that got damaged. You have the specialized face area that got damaged. So analysis by synthesis refers to this idea that you maybe can see the elements of a face, but that you can't synthesize it into a pattern that you recognize. So the prosopagnosia is a great example of, analysis by synthesis being a good explanation for why a person would have this deficit when their facial recognition area has been damaged. So some of the features of this explanation of pattern recognition is that the stimulus gets broken down into its component features for then element by element comparison to things that you already know. So the Mueller-Lyer illusion is a good example of how things that we tend to consider just as a synthesized whole are probably processed in elemental bits by our brain and then synthesized. So in this illusion, the line on the right tends to look longer to people than the line on the left. And a lot of times people will say that the reason why the one on the right looks longer is because those, those V's on the outside are like drawing your eye outward. But that's an incorrect interpretation. What is going on here is that you are looking at, on the left side, a corner of a building that's coming towards you, like the outer corner of a building, right? So you see that the black line is the edge of the building, and then the blue parts are the top and the bottom that are the what should be parallel to each other lines that are formed by the wall. Right? If you think about walls in your house, the junction with the ceiling and the junction with the floor are parallel to each other. But as an object goes off in the distance that's made up of parallel lines, as it goes off into the distance, those lines tend to converge as you go off into the distance. Think about the sides of a road. They seem to come together in the distance. The same is true with a protruding corner in your house. So if you look at that protruding corner like that, you'll see that the junction with the ceiling and the wall and the junction with the floor and the wall actually make triangles. They aren't parallel lines. They make triangles. The one on the right is a receding wall, a corner that's going away from you. And so you're getting the reverse effect where you've got the corner there in the straight line, and then you've got the junction between the ceiling and the wall forming that V shape, and you've got the junction between the wall and the floor making that inverted V. Because your brain knows, without you necessarily even having thought about the fact that in 3 dimensions this is what things look like, because your brain knows that, and because your brain processes things like walls as a series of elements that need to be synthesized for you to be able to understand them, your brain knows the thing on the left is a protruding wall and the thing on the right is a receding wall. Like, your brain just knows that. And so when it sees these two things next to each other, it says to itself, well, the one on the left is a protruding wall, so it must be closer to me than the thing on the right, which is a receding wall. Like, the thing on the right must be farther away because that's how the world works. That's how the world is designed. And so your brain just assumes the thing on the right is farther away, yet it looks the same size as the thing on the left. And therefore, the thing on the right must actually be really big for it to look this big, even though it's farther away. It's kind of related to the moon illusion that I was talking about in the last segment. So here's an example. right? Your brain knows this without you even needing to know that the thing on the left is depicted by the protruding corner. That's the blue corner in the picture on the right. And the thing on the right is depicted by that receding corner that's in the yellow part of the diagram. So let's watch that one more time, because I made this too. I made these little burgundy lines that are on the drawing on the right hand side. And then all I did was an animation that makes them move towards each other. Even as I watch it, as the person who created it and who animated it and knows that they are the same line and they're just moving next to each other, I see them looking like they're changing in size. Especially as the one on the right passes the door, I really see like almost a U-shaped pattern to the movement. And that's because as that line is passing things that are on the wall, your brain is like, oh, now it's part of the door. Oh, no, it's not. Your brain is trying to make sense of what's out in the world all the time. Even as you're learning about a visual illusion and you're hearing the mechanics behind the visual illusion and all that, your brain is still treating that diagram as if it is in fact a house. It still is trying to make this be a real world. So as you watch those go by, you see the line on the right looks much longer than the line on the left. And as they approach each other, it almost seems like they are changing in size as they approach each other in order to end up the same length. And I'm promising you that I did not do anything to those lines. They are in fact just moving on a horizontal trajectory. The lines are in fact identical. I just made one and then copied it and pasted it and then moved them where they were supposed to be. They aren't different in size. Nothing magical is happening except for that your brain knows how the world is designed, and your brain is seeing the one on the right as longer because it perceives it to be farther away. Pretty amazing stuff. So the stimulus is broken down into its component features, and then in this model, you store a feature list in your long-term memory store. You don't have to have every single template of everything you've experienced, but instead you have all these different little features of things that you've experienced. And some features are going to be shared in common across lots of different stimuli. So you can use the same feature to represent more than one thing in this model. So this makes it a little bit more tenable than the template search, because now you don't have to search through, every single template that would represent every single instance of a tree or a glass or all these different things. Now instead you just look for certain features. There are some feature detectors that have been discovered in our occipital lobe of our brain, which is the visual cortex, the part of our brain that actually processes information coming in through vision. The fact that these feature detectors for lines and lines of different orientation and for motion and all sorts of different things are present in the cerebral cortex gives a little bit of support to this theory, the idea that you might have literal neurons in your brain that are devoted to processing different kinds of features. So at least this theory is at least partially accurate. It may not explain everything about how we recognize patterns, but it definitely explains how we break down input into its component parts and then recognize those features in our brains. Now, one of the ways that we really strongly know that we have feature detectors for different kinds of line orientations, and that these feature detectors are dependent on experience, not innate, everybody's brain is developed the same way, but instead based on experience, is from research on this set of drawings. So you see on the left circle, the lines are vertical. In the center circle, they're diagonal. And in the right circle, they're horizontal. The job of the participant is supposed to be to walk backwards until the lines in one of those three panels become blurry. Now on our slide, they're already blurry, so that's really handy. When I enlarged the image, it got blurry. So so it's supposed to be, these lines are crisp, and then you're supposed to walk backwards until one of the panels looks blurry. For people who are raised in a carpentered world, which is, a lot of the world, but definitely Westerners who have been raised in houses that have very vertical walls and very horizontal floors and stuff like that, the first circle to get blurry tends to be the middle one, the diagonal lines. That gets blurry first. And that's because people who are raised in carpentered worlds have more neurons devoted to processing vertical and horizontal lines and fewer devoted to processing diagonal lines. Because in our world, in our experience, we have seen more verticals. Here's my Audubon clock. It's a goose this hour. So in our carpentered world, we have had fewer diagonal lines to sort of set up our visual system on, and way more verticals and horizontals. They've administered this test to Australian Aborigines who are living in the backcountry, and they found that in those situations with people who don't have experience with carpentered worlds, all three panels get blurry at the same time. They don't see the verticals and horizontals as sharply as a person who was raised in a carpentered world, but they see the diagonals more sharply. So they have sort of even amounts of neurons devoted to the different features. So that helps to illustrate that these feature detectors are dependent on experience. They're not dependent solely and strictly on just, genetics setting up your brain in a certain way. So the presence of these feature detectors really support the idea of, analysis by synthesis. Now, I thought it would be fun for you to see some other ways that we know that feature detectors are present and that they're based on experience. And so I thought you could watch this video about Hubel and Wiesel, who first discovered the feature detectors. So go ahead and watch that video, and I will see you on the other side.